Okay, now let's take a look at resonance. Now, resonance is another characteristic that's electronic. So let's put that down. This is electronic. And what we're seeing with this electronic characteristic is different than the inductive characteristic, but there's some similarity. It's about movement of electrons, but in this case, it's about the movement of electrons in a pi bond. That's the difference. Now remember, a sigma bond is a single bond, and if you move electrons within a single bond, that's an inductive movement. But if you move electrons in a pi bond, a double bond, or a lone pair towards a double bond, then that is resonance. And we know a lot about resonance. So I'm not going to go through all the rules of resonance in this video. I'm assuming that you've watched it, or if you haven't, you should go back and watch that one. But what I'm going to do is just focus in on the details that we need to know for this one. Now, if we have, let's say, a carboxylic acid, and this carboxylic acid has two lone pairs here and there. Okay, here's our carboxylic acid. So here's an example. Now, when this acid loses a proton, let's say we have a base and we pull off that H and we make this oxygen take the electrons. And so now we have that right there, and this oxygen now has an extra pair of electrons. Okay, so it has one extra electron. It took the H electron to itself. Now, this oxygen is negative, right? It was neutral. It's now negative, valence. You can do the formal charge if you want. Well, the idea here is that if you have an atom with a lone pair, and that atom is directly attached to a double bond, in this case, double bond O, carbon has double bond to O. It doesn't matter what the double bond atom is, but if there's an atom with a lone pair, and it's directly attached to an atom that is double bonded, then this atom that has the lone pair can take its lone pair, it doesn't matter which one, and move it towards the double bond atom right next door to it. And that would repel the double bond away. So right now I'm drawing a resonance form, but I'm skipping the one that's in the middle where you just pull up the double bond to O, because that would make a hybrid, or sorry, a contributor that's not as stable. So we don't necessarily have to always draw every contributor like we did when we learned about resonance. In this case, we're going to draw the important contributor. And so now we have a double bond here, and now this oxygen up here took up the electron, so now it's negative, and this has two pairs left. So I took one of my lone pairs, it doesn't matter which lone pair, and I made it become a double bond to the neighbor that's already double bond. And that pushes the double bond away. Well, what do we do here? Well, what we're doing is we're distributing a negative charge over a large area, right? Larger than if the atom couldn't do this. So by having resonance after it loses a proton, it's capable of stabilizing itself by moving electrons around, as we see, which means that this makes it a good acid, or it's not really strong. Remember, we're focusing on Bronsted-Lowry, pKa, strong acid, but it makes it a good acid compared to something that cannot have resonance. So if I compare this to this alcohol, and it has a base, pull off its H, well, this oxygen here is negative, has two lone pairs, now it has three. The problem here is that this oxygen has no neighbor to give electrons to. Okay, you can't do resonance because there's no double bond. And so if that's the case, this oxygen has electrons that we call localized. Okay, these electrons are local. They're local to this atom. They're localized electrons. So notice how that electron can't go anywhere. It's local to the atom, whereas these electrons here are called delocalized, right? Because you can move them around an area besides the atom that initially has the lone pair. You can move them elsewhere. So they're delocalized electrons. Now, resonance and delocalization go together. If you have resonance, you have delocalization. If you don't have resonance, you do not have delocalization, okay? So that's the trend that we're seeing here. So if I ask you which is more acidic, you're going to say this is more acidic because the molecule on the right has a more stabilized form. It has electrons that it can push and distribute over a larger area, and that makes it more stable. Remember what I said just a moment ago. I said if you could distribute electrons, it's favorable to do that, and it makes it a more stable system. Okay, so this is the idea of resonance. Now I want to take it a step further. So here's an example with carbon. Now, carbons are not acidic. Remember, their pKa is like 50 or 60. It's the bottom of the pKa chart. However, if I have, let's say, a carbon, and this carbon has H on it, I'll just draw out the H's over here. Actually, I'll draw them all out, although I didn't have to. Now, if I told you that this is considered acidic under the right conditions, you're going to say, it's carbon. How's it acidic? It is. Here's why. If I take a base and pull off this H, and now carbon takes the electrons to itself, well, we have this carbon now that's negative. I won't show the rest of the H's. So it's got this electron pair. It took one electron extra from H away from it, right? From the H to itself. And now it has this form here. Notice that this carbon here is directly attached to an atom that's double bonded. It happens to be a double bond carbonyl group, but it didn't have to be. So notice that. So what that means is that this has resonance. You could move the electrons towards the double bond, and the double bond repels away. And so what we have is another resonance form, like that. So let's say O has 2 lone pairs here, 2 lone pairs here. Now it's got 3. Okay, and it's negative. So what do? We move the charge over a larger area. And so we spread the charge, making it more stable. Okay, here's another example. So even carbon can be considered an acid under the right circumstances. In this case, where it has resonance to stabilize itself. Okay, so of course, if I compare this to propane, and I use a base, this is not an acid. You would almost never consider this. Actually, I can't even think of a condition where this would act as an acid because it's such a the pK here is like 60. Right? So this is not acidic at all. However, this one is an acid, and it's of course not as good as, let's say, an oxygen that becomes negative with resonance, but for a carbon comparison, this one is more acidic. Okay? Now, this is the trend for resonance. There's a little bit more we have to go through, but this is the general idea. Now, I want to point out one other point to you about this idea of resonance. Now, I want you to think about an analogy, because I want you to realize, why is electrons moving around so good? Imagine if, for example, you had something hot in your hand, and you're running across, I don't know, an area where you can't drop it on the ground. Let's say it's a, I don't know, whatever it is. It's something hot that you can't drop on the ground. Are you going to run with it like this and deal with the pain of and the heat on your hand? Or are you going to distribute that item back and forth between both hands until, let's say, you get to the sink or something there, you can drop it? Okay, you're going to probably do this. You're going to try to shift the heat from one place to the other. Well, when electrons are moving in resonance, what you're doing is the same thing. You're shifting that negative over to a larger area. So instead of one atom having a negative charge, you have more than one that has the negative charge. So you can shift that negative back and forth, making it more stable. That's what's happening here. That's what we're doing. Okay? So that's the analogy that I want you to think about when you think about resonance and why it's a stabilizing feature. Just think about that. Okay. Now, before we go on to this one, I want one more point to mention. Okay, very important. So, the more resonance equals more stable. Okay, now if I have, let's say, we have over here, I'm trying to think of one. Let's say we do a nitrogen. Now this nitrogen has 2 double bonds on left and right side of it. And let's say this nitrogen has an H. And then I compare